So today I'm very pleased and honored to welcome Frank Wilczek as the Albanova Colloquium speaker. And today is a special occasion. We are also having the inaugural Lisa Meitner Distinguished Lecturer as today's colloquium. So I will say a few words to introduce this. The Lisa Meitner Distinguished Lecture Series is a new series of lectures that will occur here annually, and it's organized by KTH. And today we have the first contribution in that series. Lisa Meitner was an Austrian-Swedish physicist and one of the pioneers of modern physics. So we have selected the name to honor her memory. So the early part of her career, Meitner worked in Germany, but she was Jewish, and in 1938 she had to flee from Germany and came to Sweden, where she worked here at Municipal Institute and at KTH, located right at this campus. And it was shortly after having arrived to Sweden that Meitner made her revolutionary contributions to modern physics. So she predicted nuclear fission, and she realized that enormous amounts of energy could be released in this process. So this soon led to nuclear energy, science and technology, and also soon after to the atomic bomb. So initially, Meitner was not recognized for her revolutionary contributions, and she did not get to share the 1944 Nobel Prize in Chemistry, which was awarded to Otto Hahn, who did some background experiments in collaboration with Meitner. Meitner declined to participate in the Manhattan Project. She did not want to have anything to do with developing a bomb. So she became a Swedish citizen, and she also has an element named after her, element number 109, meitnerium. So it is very suitable to have Frank Wilczek as the inaugural speaker in this distinguished lecture series. So Frank Wilczek is a very prominent scientist and one of the world-leading theoretical physicists. While he needs no introduction, I will give one anyway. So he studied in Chicago and at Princeton and received his PhD from Princeton University, and he is now the Hermann Feshbach Professor of Physics at MIT. So he has won several scientific prizes, including the 2004 Nobel Prize in Physics for the discovery of asymptotic freedom in theory of strong interactions, together with David Gross and David Politzer. But there's much more than that. He has worked on a very wide variety of topics, ranging from condensed matter physics, astrophysics, particle physics, where he has made pioneering contributions to many problems. But there's more than that. So Wilczek's writings has inspired generations of physicists, including myself. And I, in particular, enjoy his 2006 book called Fantastic Realities, 49 Journeys and a Trip to Stockholm. If you didn't read this, you're missing something out of your life. There's more than that. He has also appeared on a TV show called Penn and Teller Bullshit. And according to Penn, he was the smartest person who have ever appeared on the show. So I think that having Frank Wilczek here is an amazing opportunity and very suitable to have him to give the inaugural Lisa Meitner Distinguished Lecture and the Albanova Colloquium. And his title is Physics in 100 Years. Frank Wilczek.
Thank you for that very kind colloquium. And I'm pleased to be here. It's always a great treat to come back to Stockholm. And I'm honored to inaugurate this lecture series. I've long been a great admirer of Lise Meitner. The origin of this talk was the 250th anniversary of Brown University's founding, where they had a celebration, and Leon Cooper, the C in BCS theory, and a good friend of mine, invited me on that occasion, or invited meaning commanded me, to give an appropriate talk, which he thought should be about what physics is going to be like in 250 years. I thought about that. At first I said yes, I would do it, of course, but then I thought about it, and I realized that 250 years is a bit much. I looked back at historical models, and the best historical model for something like this is probably Newton's queries at the end of the Optics, which set the scientific agenda and had many exciting insights for the time. But after 100 years, began to look a little tired. 100 years later, Faraday and Maxwell were on the horizon with new concepts of field theory, the modern form of chemistry, Lavoisier was getting off the ground. And so many of the queries had been answered or transcended. And so 100 years seemed like a much more reasonable time scale. And that's how it became physics in 100 years. I also, following Newton, want to regard all these ideas as queries. That means you state your idea and then put a question mark at the end. Newton famously inveighed against hypotheses, against speculation, but he had a brilliant method of avoiding making speculations, which was to add a question mark at the end of his statements. Now, I'm going to talk about, very briefly, 13 different queries. The first 7 will be about different forms of unification. Unification is a grand theme in physics. But once, after a public lecture, I was asked a question that kind of took me aback by one of the audience members. I have been talking about some attempts at unification, some of the same ones I'll be talking about momentarily, and this person asked me, why do you care about unification? Isn't it enough to understand things? Interesting question. And my best answer is in 2 parts. First, there are lots of success stories. Here they come. This is a partial list. Physicists will recognize all of these. Often in the history of physics and mathematics and science in general, there have been times when great advances were had by uniting 2 different domains of knowledge that were separately mature, but didn't have any clear relationship to one another. At the time of some of these unifications, it wasn't clear what putting them together really added to the subject separately, but subsequent history justifies the idea that unification in itself can be a very important goal. Perhaps I'll just talk about one of these a little more. The most impressive example of that phenomenon, perhaps, is this unification by Hamilton in the 1810s Hamilton considered, really on the basis of mathematical elegance and just the desire for unity, that there were two descriptions of the different domains in physics: the domain of mechanics, which was based on particles and their propagation, and the domain of ray optics, or so-called geometric optics, the propagation of light rays. And he asked, could those concepts be put in a common mathematical language? Can you find unifying equations that, in special cases, describe both those situations? In that way, he was led to what we now call Hamiltonian mechanics, where the description of particles was unified with the description of light, and in particular the idea that light rays gain phase and can underlie. There's a unification of optics with mechanics. This unification, which at first was kind of a purely mathematical exercise, later, when in the early 20th century, more than 100 years later, people discovered physical commonalities between light and particles, in particular the particle nature of light, photons, and the wave nature of particles. In early quantum theory, Hamilton's mathematics turned out to be absolutely essential to get to a proper formulation and understanding of quantum theory. And the second answer is much simpler. Isn't it pretty to think so? When you have two things, one is better than two. So, with that, let me discuss the particular unifications. So one unification that is particularly ripe right now, I think, is the unification of forces and substances. That is, unification of the different forces we know about and unification of the different substances we know about. This is a cartoon which actually is also an accurate representation of basically everything we know about fundamental laws of physics. We have three fundamental forces plus gravity. Plus gravity may seem a little cheeky because gravity is a grand theory, but part of its grandeur is that we don't need to say much about it to specify what the theory is. It's the theory of energy and momentum and the symmetry of general covariance, which governs the equations of space and time, how they interact with energy and momentum. So all that is understood in 2 words plus gravity. Whereas for other forces, we have theories based on local symmetry, and we need to specify the nature of the representations that are found in nature. So here there are the strong, weak, and electromagnetic, or more accurately, hypercharged forces. And each of those forces is based on the transformations of different, or reactions to and transformations of different kinds of charges that are typically, in the case of the strong interactions and weak interactions, called colors. And so in the strong, all you need to know everything about how matter behaves is the kind of strong charges it has, the kind of weak charges it has, and the strength of its electromagnetic or hypercharged interaction. And here is the specification of those for the different kinds of quarks and leptons. Here are the names of the quarks and leptons. We also have now evidence for all 4 components of the so-called Higgs fluid, two real and two imaginary components here. They also have weak colors, and that's it. With this ugly repetition to get 3 families is everything we know about, and if you follow the rules of symmetry and spell it out, this gives us the so-called standard model or core theories of these interactions. And it's an honest representation, although it looks like a cartoon. I'm going to explain this much of it now in a unified way. This looks very scattered. I've erased gravity for the moment. That'll come back. I've erased the other two repetitions, the other two families. They won't come back, nor will the Higgs group, except because those things so far are not part of the successful unification. But even taking that simplified version of reality, which has a large chunk but not all of it, things look a bit scattered, given how powerful and accurate this account of nature is, how close it is to nature's last word. We'd like to think it has elegance and coherence that are worthy of that. And it really doesn't. It looks scattered. I like to use what I call the parable of the dodecahedron. Suppose someone, you'll notice a certain family resemblance between the standard model, as you saw it there, and this scattered pattern of pentagons. And if you don't have dodecahedral literacy, if you haven't been thinking about Platonic solids and symmetry and dodecahedra recently, you might not know what to make of this pattern. But if you do know about those things, the fact that there are pentagons, that they come together, 3 on the side, that there are 12 of them, this is sort of suspicious. This makes you suspect that what this really is meant to be is that. Instructions for having an origami cutout that you can fold up and have a nice desk calendar in the form of a dodecahedron. Now, I mentioned that that previous mutilated dodecahedron sort of was reminiscent of the standard model with its scattered pieces of matter. Could it be that there's a elegant version dictated by symmetry that puts all those pieces together? Well, of course, I wouldn't be going down this road if there weren't. And there is. When we study in detail the core theories, they're based on symmetry. Symmetry is something that the mathematicians have developed very, very highly, so we can classify possible encompassing symmetries, which would put the different pieces together, just as different pieces of a dodecahedron can be put together and rotated to make a symmetrical object. We can study the possible ways in which we can put together the different parts of the core theory, those scattered parts, into a coherent symmetrical whole. This is what you get in the most appealing version of that. There are only a few possibilities. This is the master version, based on, for experts, the 16-dimensional spinor representation of SO10. For non-experts, just behold the glory of this matter. You have, I won't be able to do it full justice, but I can give you a few pointers. First of all, notice that, what is 16? We had 16 particles before. Why 16? Why not 17, 13? Well, 16 is a magic number, and the way it reflects itself in the symmetry patterns is that we have every possible distribution of charge, positive and negative units, in fact, positive and negative 1/2 units for technical reasons, among the 3 different strong and 3 different weak colors. So in this representation, with just pluses and minus signs, you see all possible distributions of pluses and minus signs that have an even number of plus signs, and that makes 16 possibilities. Each is represented exactly once here. If we translate that into color charges, positive and negative, you get this diagram. And you may remember that there were funny numbers representing the electromagnetic charges, or more accurately, hypercharges of the different particles, which were unrelated to each other within the core theory. Now this is a strict relationship between those quantities and the other quantities that govern the strong and weak interactions. So it's very elegant. One can spell it out further to show how you get from that pattern to the exact pattern of the standard model, but given constraints of time, I won't walk you through that. Maybe someone will ask at the end. But trust me, it works. And we have a marvelous correspondence between the mathematically ideal embodiment of increased symmetry and the real thing that we find in the world. So this is a unification, for sure. Instead of 3 different forces, strong, weak, and electromagnetic, we have just one. And instead of 6 different unrelated pieces, entities, that were unrelated by the symmetries of the core theories, we now have just one. And 1 is less than 3, and 1 is less than 6, and 1 is a pretty small number. So this is definitely progress in unification. If it's true, that is. So the numbers all line up, but can we find reflections in reality for this scheme that go beyond what we put in? That brings us to the next unification. In fact, that first unification, when you study it a little more carefully, seems very dubious, because the symmetry among the different forces, if they were really aspects of the same force, would demand that they all have equal power, that they all have equal strength. But when experimentalists go out and measure these things, that's not what they find. They find that the strong interaction is in fact stronger than the other interaction, for instance. Fortunately, another big lesson that we've learned in the latter part of the 20th century is that when it comes to looking at the properties of particles, what you see is not necessarily what there is. We've learned that space is an active medium full of quantum fluctuations, spontaneous activity that's everywhere and every when. If your eyes were more nimble and could resolve distances of order 10 to the minus 14 centimeters and times of order 10 to the minus 24 seconds, that would be blatantly obvious to you. And this is a computer calculation of fluctuations in the energy and gluon fields on those kinds of scales. Made visible, of course, by translating it into ordinary color. And the most intense colors are the most intense densities of energy. And these dance. In this particular movie, there are only 5 different slides, so it keeps repeating. Reality, of course, it doesn't repeat, but is spontaneous activity, fluctuations we call virtual particles or quantum fluctuations, or zero-point motion, or vacuum polarization, all the same thing. All the idea that in space, we don't have void, but rather a medium that's active. And because of that, what we see when we look at the particles inside, we don't see them directly, but we see them through this distorting medium. Fortunately, some of us figured out how to correct for those distortions. As I mentioned before, if you actually measure at the kinds of accessible resolutions that we get at high energy accelerators today, as at these, represented by these circles at the left-hand end, you find that the strong interaction is different and stronger than the other interactions. I plotted it this way, so you have inverse coupling strength and on a logarithmic scale so that these changes look like straight lines. The message is that the strong interaction gets weaker if you make the corrections at short distances than it seemed to be at long distances, or equivalently, that it gets weaker when you study things at higher energies. And you can also calculate how the other ones work. Now, if unification is going to work, we should find that going down to really short distances, once we've made the appropriate corrections for our distorted vision, these guys all come together. And you see close but no cigar. They seem to want to come together. The strong interaction dutifully gets weaker so that it can look more like the other interactions in power. But they never quite can agree on what they're supposed to do. So, nice try. If we were followers of the philosopher Karl Popper, we could take solace at this point. Karl Popper told us that the goal of science is to produce falsifiable theories. So here we have a falsifiable theory that's not only falsifiable, but even false. What could be better? Well, what could be better is a truthifiable theory that we can make more beautiful, and then it perhaps ceases to be false. Now, I showed you that in our unification, we got down to one force and one substance. It's hard to get smaller than one and remain sane. But it's actually not one, it's two, because there's one force and one substance. That's two things. Can we make a unified theory where force and substance get unified? That's kind of an outrageous idea. It's as if in a yin-yang figure where the yin is the substance that gets pushed around by yang, the force. You found that you could make a transformation, you'd find a different perspective that's still valid where these guys change roles. Prior to about 1974, this would have seemed like a totally out there, outrageous suggestion, but in the early 70s, Julius West and Bruno Zumino primarily figured out how to implement this idea in a precise mathematical way called supersymmetry. Supersymmetry is an expansion of the world as we know it. In order to accommodate this kind of transformations, we need new kinds of particles into which the particles we know about can transform. For every force particle, such as a gluon, we need a substance particle, which is, in that case, a gluino, that has much of the same properties, the same color transforming properties, but is a so-called fermion and has spin 1/2 instead of being a boson with spin 1. Anyway, so we need those extra particles, and if we're going to have supersymmetry, if we're going to implement this last unification, and they introduce new fluctuations. There's more stuff. That stuff also fluctuates. There are also virtual gluinos, for instance, and we have to include the effects of all those and recalculate. And by golly, when we do that, it works. But do these particles exist? We don't know. If they're going to do this job of unification, they can't be too heavy. If they're extremely heavy, the fluctuations are extremely rare and don't make this kind of correction. In that calculation, I put in as sort of as light as they can be to be consistent with what we know from the LHC and other limitations. And it works. But if we push up the masses a lot higher, it won't work. So reading it the other way, the fate of these ideas is in the hands of the LHC, and we'll soon know whether these are on the right track or we've been misled by this hope for tremendous unification. It gets better, or the stakes rise further, when we bring in gravity, which so far I left out. Gravity is another force, is the other fundamental force we know about. It's based on similar but significantly different principles of symmetry. And we can compare the strength of gravity with the other forces. The other forces are based on quantized charges, so it's straightforward to compare them. They all have, at some level, 1/r² forces, but so does gravity. Gravity, however, responds to energy. When we want to compare, and it doesn't have a quantized charge, how can we possibly compare them? Well, we can compare them because at large energy, where we want to make these comparisons, energy dominates any contribution of the mass of the particles that we're comparing. And so we can simply put in the appropriate energy to calculate the strength of the force of gravity. If we compare gravity at the currently accessible distances to the other forces, we get a tremendous discrepancy. The discrepancy between the strength of the strong and electromagnetic forces is about a factor of 10. When we turn to gravity, it's not 10, or even 10 times 10, or even 10 times 10 times 10. We have to go way beyond the known universe, multiply by 10 40 times until we get to the strength of gravity. But because it responds directly to energy, it comes roaring in at the last moment, and it turns out that it fits pretty much too. So this indicates that if we can make the unification of forces and substances, gravity will happily cooperate as well. We'd like to get more evidence for the quantum nature of gravity. That's hard. We'll also, in 100 years, have gravity waves opening up a new window into the universe. That I think we can rely on. It may even be that we have both cosmological gravity waves leaving their imprint on the microwave background, as well as gravity waves in the conventional sense from astrophysical sources. These are things that are boiling up right now in physics, and by 100 years from now will be a big window into the universe. One thing that's very disconcerting if you start to think about space and time and what it should look like in 100 years is how conventional it's looked up to now. We still base our models on fundamental models of physics on real numbers. How did real numbers come about? Real numbers came about by studying the measuring process. You have a ruler, you measure something. If you want to measure something smaller, you cut the ruler in half and make a smaller ruler. If you want to make it smaller, you keep doing that. And the model is that the numbers that correspond to this process of being able to infinitely well subdivide things are the real numbers. But we've learned in physics that that's a way too naive a picture of how you measure distances. Nevertheless, the real numbers have persisted. When we come to supersymmetry, you need a new kind of number called Grassmann numbers. I predict that in 100 years we'll be dealing with other kinds of numbers, perhaps infinitesimals, which are a beautiful branch of, with a beautiful invention of mathematicians that so far have not invaded physics. So those are three unifications having to do with different aspects of physical law, and those unifications, I would say, are relatively mature. We can point to specific experiments that will probe them and look forward to new information in a few years, and I think tremendous progress can be confidently expected in 100 years. Now I'd like to discuss a few kinds of unification that are more iffy, but I think we're looking for weak points, we're looking for places that are promising to pursue further. I've tried to identify some. A long-standing debate that goes back to the ancient Greeks, but came to a head in the early days of the scientific revolution, was the debate between perfection, geometric perfection of the structures that govern the universe, and a kind of static picture of what governs them. This beautiful model is Kepler's model of the solar system, where the different planets get carried around on spherical shells, and the spherical shells are circumscribed and inscribed within and without the 5 Platonic solids. So Kepler started his career in astronomy by making this discovery, he thought, and was enraptured with the idea that God is a geometer and constructed the solar system using these perfect geometric objects. Kepler himself was an honest man and worked very hard to compare his model with observations. He never quite recognized that it didn't work, actually. He did discover that planetary orbits are ellipses, but not circles. He thought that might have to do with the thickness of the shells. And even in his later works, he persisted with this model. But the fruit of that work, as far as we're concerned, and the long-term future of physics, was Newton's understanding, which was quite different. Newton's understanding of the solar system is based on dynamical laws, where you study the smallest elements of motion and how they change in time. And those are the basic laws, not the laws for the global structure of things, but the dynamical laws that tell you how things change in time. So according to Newton's physics, the shape and size of the solar system is rather accidental. It's the underlying gravitational law that's precise. And now that we know that there are not just 6 planets, but more, and that there are many other solar systems that look quite different, it's hard to avoid the idea that Newton was basically right, that the dynamical laws are the fundamental laws, and the structure is kind of accidental. The strategy that emerged, therefore, of separating our description of the world into 2 components, dynamical equations on the one hand and initial conditions on the other, has dominated physics since Newton's time, and it's served us extremely well. And it's still the way fundamental laws work in our core theories. Nevertheless, if we're seeking unification, it's a place where we could do better. Moreover, there are specific motivation from physics to think that this separation is very unnatural and has to be superseded. In the theory of relativity, we learned that there are symmetries, transformations that leave the laws of physics intact, but interchange the roles of space and time. Minkowski famously said space and time will fade away and be replaced by space-time. And the separation between initial conditions and dynamics now seems very unnatural. Initial conditions say you pick one time, anything goes, and then you evolve things from there. really, if you take the relativistic God's eye view, looking down on space-time, it's just one thing. You shouldn't be making separations. Herman Weil, one of my great heroes, felt this very strongly and wrote poetically about it. I turned one of his more poetic passages into an actual poem, and here it is. The world simply is. In my consciousness, tethered to my brain and body, fleeting images come to life. Of the world, samples only. The world simply is. It does not happen. Another unification that is hinted at in Weil's books, and I think is something that physics should strive towards, but that has not been accomplished, is that we have two kind of basic principles at the root of our understanding of the world. We have a framework, which is quantum mechanics, whose axiomatic basis is not entirely satisfactory or even clear, but part of it is that there are so-called commutation relations, that different quantities like positions and momenta are not represented by ordinary numbers, whose multiplication is commutative, but obey specific non-commutativity relations. The other great ingredient of our fundamental theories of nature are symmetries, and when we formulate symmetries, typically the way we formulate them is to say that there are operations that we can combine, and the rules for combining them lead to commutation relations, lead to funny relations that have the same suggestive form as the relations of quantum mechanics. So but at present, these things are postulated separately. There's no crosstalk between them. This is a unification begging to be made between symmetry and the principles of quantum theory. Can quantum theory be understood as a theory of symmetry? Is that symmetry part of the wider varieties of symmetry that we use in other places in our fundamental laws? Another unification that seems right is but has not been completely consummated, is the unification of information and action. In the current formulation of physics, I think it's fair to say the foundational concept is action. Action is what appears in path integrals as the measure. Action is the thing that's invariant under fundamental symmetry transformations. Action is implicit in Hamiltonian mechanics, which quantum theory relies on, as I mentioned. This is a kind of joke which I should elaborate on for those of you who may not be familiar with what action is, and to put it in more context. In Newtonian mechanics, the fundamental concept was force. And that served Newton very well in formulating his laws of motion and so forth. But great progress occurred, especially in the 19th century, when the notion of force was kind of superseded by the notion of energy. Energy is the integral of force, but not all forces can be derived as derivatives, but that is starting from energies and taking derivatives to get back to forces. Only so-called conserved forces can do that. So when you ascend from forces to energy, more of the fundamental assumptions are built in and have a priori basis, are more deeply integrated into the theory. Action takes that one step further. When you go from energy to action, action is the integral of energy. And not all theories that have conservation of energy can be derived from action, or that have an energy principle from which you can derive forces can be derived from actions. It's only the ones that lead to the Hamiltonian form of mechanics that do that. But the Hamiltonian form of mechanics, we've learned, is very fundamental, so that action, even though it's not the most general concept, appears to be the one that nature likes. Similarly, in the principles of electrodynamics, there are 4 Maxwell's equations, 2 of which are Faraday's law of induction and the principle, Gauss's law for magnetism. Let me say something about Faraday's law of induction. When Faraday discovered that experimentally, that changing magnetic fields can produce electric fields, it was a great discovery. It was an experimental discovery. Faraday thought he was discovering something about the world that wasn't obvious or automatic. But in today's understanding of Maxwell's equations, Faraday's law is a mathematical identity. These basic principles tell you that there has to be a way to formulate electromagnetism that's consistent with Hamiltonian mechanics, that can be based on an action principle. That requires introducing potentials, and once you introduce potentials, Faraday's law becomes a mathematical identity. So Faraday thought he was discovering how electric and magnetic fields behave. He was really finding out that action is where the action is. In any case, given Planck's constant, which is a unit of action, as a unit, then action becomes a purely numerical, dimensionless in the sense of dimensional analysis, quantity. The world action, which governs our fundamental laws of physics, is therefore a specific numerical quantity that governs the basic operation of the physical world. One would like for such a basic quantity to have profound independent meaning. This is something that we'd like to unify with other profound ideas about how the world works. What other idea is there? Well, information is another dimensionless quantity that we've learned how to measure thanks to the work of Claude Shannon and others, that plays a large and increasing role in our description of the world. The question for unification is, can one unify action with information? Actually, this is very ripe, I think. Nowadays, many treatments of the microphysical origin of entropy, which is another related quantity, and of the foundations of statistical mechanics in general, begin with discussions of information and ignorance, which is sort of the opposite of information. There's a strong formal connection between entropy and action that, for experts, arises when you do the Euclidean imaginary time path integral formulation of partition function. So there's a formal connection, which is quite strong, although a little obscure to derive, between entropy and action, and a strong formula, a very strong connection. I would say it's fair to call it a unification of the concepts of entropy and information. So the missing link is that we want to make, in order to connect information and action, is that we want to make that relationship between entropy and action, which is purely formal and abstract and tricky to derive, more clear and intuitive and deeper. Finally, among the unifications, we discussed the unification of mind and matter. Here is a complex system with striking emergent properties. It's a system you find within your head. It's a neural net. Physicists supposedly are very good and have developed many techniques for discussing complex systems with emergent properties. Can we figure out that one? Over the course of the 20th century, science has reached a molecular level description, unifying life and matter for metabolism and heredity, mind is the remaining frontier. If we could do that, combined with the idea that we've related information and action, we would have found that physical systems become more mind-like, that the action is underlain by information, and with a molecular level understanding of mind, that mind becomes more matter-like. And the visions of people like William Blake, that you can figure out how the world works, and that the world works according to mathematical principles, as though it was designed, will come to pass. Or John Wheeler's diagram of the emergence of mind from matter and mind coming to understand matter. So let me summarize those discussions on unification with a set of predictions, some of which I've at least partially justified, others that you can find in the longer version of these of this discussion that has appeared on the archive. Another prediction of the unification of forces is that baryons will decay, protons will decay. That's going to happen. That will be observed and will lead to a rich phenomenology. Supersymmetry, which enables this beautiful unification quantitatively, will be observed, maybe very soon, maybe it'll take a while. And it too will lead to a rich phenomenology. There are many decays, many particles. This is not just, each of these opens up a new world. I didn't even mention it, but the nature of dark matter will be revealed, I hope in much less than 100 years. And in fact, maybe in a moment. In fact, oh, there it is. And tangible consequences of quantum gravity will be identified and observed. I didn't elaborate on this, but one consequence of supersymmetry in many realizations is that gravitational interactions can be visible. What are called non-minimal couplings would be visible. Physicists will know how exciting that is. New kinds of numbers, including some form of infinitesimals, will be used to describe space and time. It's really scandalous that real numbers, which were idealized from rulers and cutting things up, are still the basic way we formulate our laws. Gravity waves will be observed and become a powerful tool in astrophysics and cosmology. The fundamental laws will no longer separate into initial conditions and dynamics. Information will appear as a primary ingredient of physical law. Quantum mechanics will be formulated as a fundamental symmetry principle and integrated together with other such principles. And biological memory, cognitive processing, and emotion will be understood at the molecular level. A lot's going to happen in 100 years. I'm taking resveratrol, trying to take care of myself. I hope to see a lot of it. Let me turn then from unification to, which is in a sense extending the laws we know in attractive directions, to using the laws that we know, pushing them harder to do exciting things, technologies. Arthur C. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic. And I would like to add a scholium to that, which is that nature's technology is very advanced. Furthermore, nature is a very kind magician. She lets us examine her tools, and by learning from that, we can become magicians ourselves. So one theme that's close to my heart, and I've been working very hard on recently, is the idea that as we've learned about the law of physics, we learn that the way nature has equipped us, evolution if you like, has equipped us to perceive the world, is nowhere near doing justice to everything that's out there. Our sense of vision is based on taking three average, if we're not colorblind, and we're talking about vision during the day, we take three averages of the electromagnetic intensities. We throw away within a narrow band. We throw away polarization. We throw away infrared and ultraviolet that's out there. And as I said, just take three crude averages. It's as if when we listen to music, we could only hear three notes. And if you played chords, you would only find that they're three-dimensional. You'd lose information about the separate notes being played and just get three samples. Lots of chords would sound the same. There is much more information around. This is proved by the existence of other biological creatures that have many, many more different kinds of receptors. The champion of all things is something called the mantis shrimp. The mantis shrimp has, depending on which species it is, something between 12 and 16 different receptors that are much more fine-grained within the visible, but also go beyond the visible into the ultraviolet and the infrared. So there's something interesting. There's more about the world you can learn that's of interest to mantis shrimps, obviously, by doing this more extended processing. It may be that what mantis shrimps are especially interested in is what other mantis shrimps look like. But in any case, we can imagine humans that by various sorts of gadgetry have sensitivity in the ultraviolet or finer grained within the visible. Let me illustrate that on a simplified case that's easier to visualize than you can do in software, which is the difference between colorblind perception and three-color perception. So this is one of the famous Ishihara tests. Those of us who can see three colors will notice that there's an 8 here. But the most common form of color blindness is what's called red-green color blindness. And essentially what happens in red-green color blindness is that you should, in an RGB display, replace both R and G, red and green, by their average. Colorblind people with red-green color blindness can't tell the difference between images that have been treated or not by taking those averages. So if you take this Ishihara test and you apply the algorithm of turning red and green into their average, you get this, and you can appreciate how the colorblind person has a difficult time finding an 8 in here. But we can attempt to restore the information. How? We want to make it in a way that's perceptible, that's systematic, and that's true to the image. How can we add extra channels of information? Well, we can exploit the dimension of time by using time-dependent textures. In the channels we have, we can put in information about the channels we don't have. So, for instance, here's the 8, and now we put in time-dependent shimmering that depends on the difference in the original image between red and green. Put that shimmering into something that still obeys the constraint of red and green being equal, both being replaced by their average. We can do it in such a way that the information about the 8 is restored. And, as usual, Yeah. If anyone wants to see a more of an impressive display, I'll be happy to show you this and many others later. Okay, so that was one technological advance. I'll very quickly mention a few others. Making things in the micro world. We have the equations for chemistry. We have the equations adequate to design materials. The equations of our core theories have been tested with greater accuracy and under much more extreme conditions than are necessary for any practical application. In aerodynamics, people have replaced wind tunnels with computer farms. When you design airplanes, you no longer use wind tunnels, you compute. We should be able to do the same thing with chemistry. That would be enormously useful. You could start to make things like, think about things like this, and also how to make even a God detector. We also have now accurate equations, again, with 1% and constantly improving accuracy for the fundamental components of the strong interaction. Recently, a great milestone was passed. Kept people using lattice gauge theory to simulate the equations of QED plus QCD. We're able to give a convincing calculation of the proton-neutron mass difference from first principles, a very basic parameter of nature that we finally understand from microscopic, profound principles. So that kind of control of the nuclear world opens up the possibility of doing things that that have proved to be extraordinarily powerful in the atomic world, making, I should say, when I was a student, my atomic physics was kind of moribund. Nobody, it was this tired subject whose great days had passed, supposedly. But discoveries of lasers, but since then it's flourished tremendously, surprising many people, but of course not the atomic physicists. Now we can aspire, and the reason it was possible to make so much progress is that we had firm foundations and increasing abilities to calculate. Now we have a similar situation, and perhaps we can do justice to the discoveries of Lisa Meitner, that nuclei can be manipulated, and we can use that to make ultra-high powered lasers, ultra-high energy lasers, and ultra-dense energy storage, for instance, as well as understanding things like supernovae a lot better. Moving up a little bit in scale, the mesoscale. Today, computers are essentially two-dimensional objects. They have to be made in clean rooms at great expense, and they're very delicate. If you do the wrong thing, you can destroy them irreparably. You drop them, put them in a strong magnet, for instance, or drop them in your bathtub. I've done all those things. There's no fundamental physical reason why for any of those things. We can imagine, and we see in the biological world, in fact, I'm looking at them, examples of computers that are three-dimensional, fault-tolerant, and self-repairing. Wouldn't it be wonderful to have combined those virtues with the speed and reliability of semiconductors? And for computers, so in general, we could imagine self-assembling and self-replicating biomachines. Scaling it up, I think within 100 years, the visions of science fiction writers, as particularly Olaf Stapledon, who if you haven't read, you should, will start to be realized. Olaf Stapledon already in the 1930s, was writing about a history far more advanced than my mere 100 years, speculating about the far future of humanity and, in fact, of life forms beyond humanity. One thing he mentioned and elaborated on quite a bit was the possibility of turning whole planets into gigantic brains. Well, I think we can do it. And within 100 years, that'll be challenging, but maybe asteroids first. Freeman Dyson has also proposed that advanced civilizations will make much better use of the energy coming out of their star, in our case, the sun. The Earth, as seen from the sun, is really, really tiny. It subtends a tiny angle at the sun. All the light from the sun that doesn't impinge on that tiny angle is lost to human use. And yet, even the part that does impinge on us is 40,000 times more than we make use of in our economy. So we have an energy crisis, not because the energy isn't there, but because we don't know how to extract and store it cheaply. But eventually, and hope better be soon, that'll happen. When thinking about making the so-called Dyson sphere that would actually capture all or significant part of the sun's energy, I reverted to 250 years. That would take a long time because the sun is very, very big. But we better get started. And the idea of capturing a large part of the sun's energy and using it in clean, efficient ways will enable us to overcome, hopefully, the challenges of pollution and climate change, and is extensible for the foreseeable future into as humanity becomes more ambitious in its engineering progress. The human body, we're distributing it, I think, over time, right? So let me very quickly round this up. In the future, it's already happening that our brains experience distributed intelligence. We can sense things far away. We can look at coffee pots far on the other side of the world on the internet. And that's going to get better and better. Human bodies are not well adapted to space. Manned space travel is very, very difficult. The pioneering efforts, if we really want to get far away and start expanding the human sensorium, are probably going to be artificial intelligences, but they will pioneer, make things nice, and then we can follow. I've shown you that the future looks fantastic in many ways. Our descendants will be much more powerful and much more intelligent and much more empowered than we are. We might worry that they're going to get arrogant. But if we look towards the past, there is at least the possibility that there'll be something I call emergent humility. Going back to Isaac Newton, Newton was not a modest man, but he was an honest one. And after a life where he found remarkable truths and speculated about more, as I mentioned, he said something like this: "To myself, I seem to have been only like a boy playing on the seashore, diverting myself, and now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." And that's the feeling I get, and that's what as I learn more and more about the universe and think more and more about what should be possible, what we don't understand. And that's what I think even our descendants who know much more and are much more powerful will come to feel. So I think that's an appropriate place to stop. Thank you.
Thank you very much for this brilliant. So let's take a couple of questions.
Well, Professor Wilczek, what would be your estimate for the timescale of the emergent humility slope here?
It's already all around us right now. I think, well, emergent humility is a very special thing. It's not the same as being humble. It's valuing what you've done at its value, which may be very great if you've expanded human capabilities and human knowledge. But at the same time, realizing how much is still on the table, and that each time we learn how to do something, we begin to sense possibilities that haven't yet been explored. And I hope I've conveyed some of that. So, although this might seem like a wildly ambitious and freewheeling, loose talk, my feeling as I was constructing it is to realize, gosh, how much we don't know and how we're in so many ways at the beginning of what we can do and have only scratched the surface. The more we realize is possible, the more we realize how little has been achieved. Yeah.
Thank you very much for this inspiring talk. And I'm an experimentalist, so I would like to ask an experimentalist question.
Yes.
You mentioned LHC, of course, as the high energy frontier. I mean, what would you say would be appropriate experiments doing on other frontiers to achieve or obtain some of the fundamental issues you have talked about?
Yes, well, one section, in fact, one entry I didn't get to talk about because Betsy was getting antsy. Relates to that question, so thank you for it. A frontier that I find absolutely fascinating is the frontier of constructing quantum minds, quantum computers. This is related to two themes, one of which I mentioned before. There are essentially quantum notions of history, inference, and causality that are different from the classical notions that need to be developed more. But, and there are plans, there are different proposals, none of which has been shown to work in the sense of being scalable and realistic engineering, for making computers that work on fundamentally new principles that exploit the principles of quantum mechanics. In ordinary computers, the state of the computer is an array of zeros and ones, a very big array, but a definite array of zeros and ones. In a quantum computer, you can have several different configurations at once, in fact, many, many, 2 to the n if you have n bits, n qubits. And you don't choose one and then go from one to the next, to the next, to the next. Rather, you have superpositions. So it's an enormously bigger space that you explore. And then many new possibilities open up. Quantum computers evolve according to unitary evolution, which is reversible, so they can manipulate time. They can put, since everything is above the board, they could also have subcomputers or babies that are displaced in time from each other by definite amounts. They can embrace contradictions because different parts of their wave function could represent opposite answers to questions, for instance. And most visionary of all, quantum computers could understand quantum mechanics. So one great endeavor of experimental physics that has many facets that could easily occupy several colloquia is the challenge of making a quantum computer, making a computer that would actually realize these dreams. One thing that's appealing about it is that there are many sub-problems that are interesting and challenging in themselves. For instance, one that I'm very fond of is that a major road that's been talked about to making a quantum computer is by exploiting unusual properties of quasi-particles inside materials that have a topological nature, so that makes them robust, and in particular so-called anyons and fractional particles. That would be very interesting. And if you want to ask me what are the the three experimental goals that I would look for, we can mention that. I mentioned gravity waves. That's clearly great, and it's almost there. We need to find out what the dark matter is. So in particular, we need to find axions. There's some very specific things, and for instance, we understand a lot about the violation of time reversal symmetry.
Electric dipole moments?
Yes, electric dipole moments is a wonderful, if I were an experimentalist, I think that's what I might do.
I'm gonna do that.
There you go. All right. And the LHC, as you mentioned, they have to find supersymmetry, and the solid-state physicists have to demonstrate convincingly what's surely true, that there are new possibilities for quantum statistics, and you can start to use them anyhow. So I have an agenda.
Yes, I have a kind of related question, and I think a very important question. Who will do physics in 100 years?
Who will do it?
Yeah, who will do it? Will it be we? Or will it be some?
Well, probably won't be me, although I have.
I mean, looking on artificial intelligence.
Whether.
Things.
Yes, I think, well, artificial intelligence is advancing. It's become very good at some things, like playing chess, for instance. No human can compete with even relatively modest computers successfully at chess anymore. On the other hand, there are things like, primarily in fact, I think, associated with sensing and interacting with the world, particularly visually, but also in other ways, that artificial intelligence at present is very poor at, and progress in those directions has been disappointing. What I think, and so it's hard to predict how long it will take for integrated systems.
Will that be space for us, for the physicists?
Sure, well, that's what I'm getting to. Yeah, I think for the foreseeable future, probably 100 years from now, there'll be much more intimate synergy between machines and people in doing difficult problems. For me, that's already a reality. I can't imagine doing physics without the kinds of things I do without Mathematica, without the tools of computers. Even writing papers, nobody writes and without implements, my vision would be much poorer, and I wouldn't know what time it is. I wouldn't know how many flights of stairs I've climbed today. I think we can look forward to much more intimate contact between people and intelligent machines. I think the hybrids will be recognizably human, but much more empowered humans, and those will be the physicists of tomorrow, and even in 100 years. In the long, well, I'll leave it at that. I only need to talk about 100 years.
So with that, I think we should thank Frank once more.